So welcome to this presentation, which is the opening presentation in the Quantitative Systems Pharmacology week day 3, which is focused on uncertainty analysis. And I'm very happy to be here and talk about this highly interesting area, which I have worked on for many years and use in all of my projects. So in the presentation, I will talk about all steps of analysis, from analysis of data to integrating resulting submodels to using models in various types of end usage situations. I will talk about uncertainty in all of these steps and central on digital twins, which are personalized models for patients. And the subtitle here is why and how uncertainty needs to be done in all of these steps. And these digital twins is captured here in the logotype of our spin-off company, which is called Sund, which is the means healthy, but it's also part of my last name. And apart from a spin-off company, I'm located at Linköping University, at the Department of Biomedical Engineering, and this is our logotype for our research group, which has two parts. The first part means that we study mechanistic models, where you can look inside and see the mechanism, so it's not machine learning. And the second part is that we really can determine the well-determined parts. Here they are represented by this core here in the middle. And for this reason, I call those well-determined predictions core predictions. And other predictions that are outside the core here are just suggestions. So, and in practice, we also do hybrid modeling. I will not talk about this today. So, one more slide of just very zoomed out what I do in general. So I've been working for 20 years developing and publishing models together with collaboration partners for all of the main organs in the human body. We put this together into an interconnected general physiological model for the body as a whole. It's personalized into a digital twin, and we have a software, a spin-off company, to turn this into end usage. And this slide also summarizes my understanding of quantitative systems pharmacology. And I understand this as the combination of PBPK models on the whole body level and systems biology models, which are describe detailed intracellular processes for the different organs. The main steps are outlined in this slide here. And the first is to test the subsystem. So you have some data and you have some hypotheses. We translate the hypothesis stated in words to ordinary differential equations, which is fitted to data. If this fit fails, then we reject the hypothesis, which needs to be reformulated. And otherwise, we use it to identify predictions that leads to model-based experiment design. And once you have done successful predictions a couple of times, then you can move to the next step, which is to integrate or translate this to the whole body level. And once you have done that, which also is a modeling problem, then you can use it either for the validation step or to help to sell drugs. So here you see comparison between model simulations and data, which are the dots and line respectively, for healthy controls, type 2 diabetes patients, and you can simulate the improvement. And this you can use as a basis for validating the drug, but also as an argument for helping patients to know that they should use the drug. And in all of these steps, uncertainty is critical. So let's start with the first step, identifying submodels. So in this particular example from 2010, we had 4 hypotheses and some initial data. And all of the 4 hypotheses could explain the data. So we are now in the upper loop. And then the first type of design that we did was to have unique and different predictions. Here they need to be well determined, so they need to be these core predictions, and they need to be different between the hypotheses. And then we can guarantee the experimentalist that at least one of the hypotheses will fall because they are uniquely determined and they are different. So they can't both be right. And it turned out that it was the first one that was wrong. And then the second type is if you don't have that many core predictions and you want to identify the parameters better, then you should measure something that is as uncertain as possible. Then you don't reject any hypothesis, but you will identify the parameters better. And once you have that, you can do more discriminatory design. And finally, you can, when you have a single model, you can do validation steps. And here we did this and ended up with a combination of the 4 original hypotheses, which could explain all of the data and that could also predict what happens in a new experiment. So here we went back and forth 5 times. So I give this the Systems Biology Index 5. So here we have, so before moving into the technical details, I just want to have a very conceptual slide where you here see simulations. Each line here is a simulation with from parameters that describe the existing data in an acceptable way. And then a core prediction is simply one where all of those simulations are very similar. So here that happens after some time in the simulation, but it could also be for another state, for instance. And if it's not a core prediction, it's just a suggestion. And the key thing is that if it is a suggestion, then it's basically just something that you could lie on the beach and say. That's why in the beginning, when I wanted to argue for when people didn't really do any type of analysis, uncertainty analysis, then I used this term a lot to sort of give the derogatory statement that if you don't do uncertainty analysis, you are just giving it could be like this, could be in some other way, and it's a very, very weak statement. But if you have done this analysis, then you can either test or discriminate between models by core predictions, and then they should be different for the different hypotheses, or you can identify the parameters better by measuring here. Okay. So with this little conceptual introduction, let's go back to the example. So this was the resulting model. Insulin binds to the insulin receptor, which was a part of the next paper, which identified how insulin signaling goes wrong in type 2 diabetes. And this was based on lots of data. Here again, diabetes and healthy controls, data and simulations. Same interpretation as before. So let's just say one of those intracellular responses and see that this model is part of a multi-level model that describes organ-organ crosstalk. And this particular model is actually approved by the FDA. And I will come back to this because their new very general guidelines for when models can be used for approval processes is highly centralized on uncertainty analysis. And finally, our digital twin model is also describes long-term responses like weight changes. So it's multi-time scale and multi-level. And here again, you see uncertainty here, which are the gray areas. And if you have data, then and if you estimate the data, then it's sort of the same area as is spanned by the uncertainty in the data. So how do you do this in practice? Well, the preferred approach, if you can do it, is to use some kind of profile likelihood based method, where you pick one parameter or prediction to do the analysis for, and then you take a value of that and you optimize all of the other parameters and you find the best agreement with the data. So you take some cost function, which typically is the log likelihood function, or the minus the log likelihood function, and then you use a constrained optimization to ensure that the optimization fulfills this value. So either the parameter, if it's just a parameter, you can just set it to a value and it won't change. So remove it from the optimization. But if it's a prediction, then you need to use constrained optimization. So you can, for instance, add the punishment to the cost function, which has a very high cost, and then the optimization will prioritize and only pick parameters that fulfill this. And then you look at the resulting likelihood function or cost function. If this is non-acceptable, so if it's above the cutoff, if it's a cost function, then it's not part of the confidence region. So you get these type of curves where here you have a parameter or a prediction, here you have the cost, and the optimum is here, and then you step away and you optimize, step away and optimize, step away and optimize until you reach a cutoff. And then you might have these type of problems that it goes up and down like this. And typically then you don't want to give two confidence regions, but you want to have not a shaky curve like this, because then it's either that it has a weird nonlinear behavior or that your optimization hasn't really succeeded. If you have this type of spikes, typically your optimization hasn't succeeded. So you can look at these curves and see that here it seems like it's just going up. So this is a more sound lower value and upper value for the confidence interval for this particular prediction. If you want to use statistical tests, which also is a good idea, and they should typically go hand in hand, you can either use some chi-square based test or some other statistical tests just to test the quality of the model, or if you want to follow the full recipe of profile likelihood, you start with the optimum and then you see how much above the optimum you can go, and then depending on if you just want to ensure that each individual parameter lies within the confidence interval 19 out of 20 times, so 95% of the times, or that all parameters lie within the confidence interval 95% of the time, you get slightly different cutoff. So this is more conservative than this one. So this is the inverse of the cumulative chi-square distribution, and this is the degrees of freedom. Another good approach, if you can't use this, or if you are a Bayesianist, then you can use Monte Carlo sampling. And the most common approach is to use Metropolis-Hastings, where you have some prior belief, you have some currently visited point, you have a tentative point, and then you pick this tentative point if the new cost is lower than the previous cost. So if it's an improvement, you always pick it, and otherwise you pick it with a probability, and the probability decreases as you go to worse and worse points in parameter space. And in that case, in that sense, you will get a point cloud that approximates the true level curves in the cost function landscapes. So you have the most points here in the middle, where you have really good cost functions or low likelihoods or high likelihoods, sorry. As you move away, you get less and less frequently visited areas. And then this point cloud can be mapped to any property of interest. So either just look at the parameters, and then you put some cutoff in this landscape and you have just the parameters, or you look at the corresponding simulations and you look at whatever property you're interested in. However, also these methods and this assumption have problems if the model is too unidentifiable, because then this process will not converge. And you can actually test if you have that problem, and this method compares the profile likelihood curves from the Bayesian analysis with the frequentist analysis, as described in this paper. One of the reasons why I advocate for the frequentist profile likelihood based approach is that is designed to really get the boundaries. So sometimes it's difficult to really find the boundaries, and then The simplest approach was just to find parameters that you encounter that are acceptable during the optimization. That will give a comparatively small prediction uncertainty. Monte Carlo sampling will give a bigger uncertainty analysis, but it's not defined to really find the extremes. And here you see that this is in log scale, so this is actually almost an order of magnitude wrong here. So profile likelihood is by definition better, or at least as good as Monte Carlo sampling is at really finding the boundaries. Finally, if you don't want to use, or you can't for some reason use either of these two, you can always use bootstrapping, where you have some original data series, you create bootstraps either by sampling with replacement or by fitting a model and simulation using some kind of noise in the process to generate bootstraps. And then you not only have your original value or property here, theta, but you have for each bootstrap you have a new value, and then you have the estimated property with the distribution. So the distribution or the uncertainty comes from the distribution of these calculated values from all of these different bootstraps. So this is very generally applicable. If for some reason you can't use the other ones, you can always use this one. Slightly less stringent and unnecessary if you can use the other ones, but it's still okay, I would say. So then coming to some approaches that I would advise against. One of them is structural identifiability analysis. And I have two examples to illustrate the two types of problems. The first is that if you do structural identifiability analysis of a larger model, so for instance, this is a model for glycolysis where we have 30 states and 60 parameters. You can use modern approaches and solve these type of problems. And in this particular case, we did that for a glycolysis model, for this glycolysis model, where we assume that, or where we actually only can measure with a high time resolution one value, which is NADH, which you can measure via fluorescence, so it's with an unknown scaling factor. And despite this very, very complex model and only being able to measure one model property, one state, the transcendence degree, so the number of parameters too many that you have, according to structural identifiability analysis, is 4, meaning that it says that you can, in principle, identify all parameters except for 4. Or if you put 4 parameters that are the right type of parameters to fixed values, all of the other ones will be identifiable. However, in practice, if you would do a practical identifiability analysis, you would come to the conclusion that maybe there are 4 parameters that you can identify. So it's like the other way around. So this means that instead of estimating all but 4, there are 4 that you can identify. In other words, the conclusion from structural identifiability analysis is that you have an almost completely solved problem, but in practice you have a widely unidentifiable problem. So structural identifiability analysis misses the biggest part of the actual problems, and it doesn't even imply practical unidentifiability if you don't have structural unidentifiability. So it's not even necessary. So if you have a problem where you have 2 processes like this that appear in the same way, so P1 and P2 are structurally non-identifiable, still, because you can identify the sum of P1 and P2, you can, and they are both positive, which they are in systems biology, you have an upper boundary for the parameter, so it's practically identifiable even though it's structurally unidentifiable. And in the same way, you can also have a lower boundary by some reparameterizations. So it's neither necessary nor sufficient to have structural identifiability. So simply don't do it. It's very beautiful mathematics, but in practice, it's not what you should use. So what about sensitivity analysis and Fisher information matrix? This is widely used, and I really advise against it, because it assumes that the cost function looks like this. it has an ellipse-shaped form, which you have if you have structural identifiability and informative data, so you don't have problems with unidentifiability, practical unidentifiability. If you have ideal conditions, then it will look like this, and then the theory holds. But if you have banana-shaped parameter dependencies, or you have other type of problems with unidentifiability, then it doesn't work. The theory doesn't hold, and therefore you have to assume identifiability to prove it, and it will typically miss many problems that you have with identifiability analysis. So it's really doing things in the opposite order. So here is just a very, very simple example to illustrate this point, where you have an additive and a multiplicative dependency between the parameters. So you have some data here, and the data looks the same, and the only thing that differs is the dependency between the parameters. Then in the first case, where you have the additive dependency, then the Fisher information matrix will say that the eigenvalue is 0, so you can't invert it, and therefore you have problems with identifiability analysis. But in the multiplicative case, you have this banana shaped, and it will, if you do a local approximation, it will look like finite ellipses, and therefore it will not detect, so it will not find 0 eigenvalues. So don't use sensitivity analysis as an identifiability analysis, but if you want to do sensitivity analysis, you should use identifiability analysis of the sensitivity analysis. So finally, some few words about the last two steps as well. So for the translation into multi-level module-based models, what you should do is to find modules where you have known inputs and outputs, and where you have outputs within a range. So this is the acceptable uncertainty range. And this can be, for instance, if you have arteriovenous difference data, or if you just have simulations from the top level model, and you know that as long as the input to the model gives this output, then it will work together. Then each submodel becomes an isolated modeling problem, and you can really prevent propagation of error between the models, and you can have a lower uncertainty of the multi-level model. And you can also have different model versions that you choose between, and it won't affect the crosstalk, but it will affect what you can analyze within each organ. And then if you want to use the two last steps, if you want to use it in practice, then FDA has published these guidelines. But the first is just to see that you solve the simulations correctly. This is typically not a problem. And then you need to do this validation, you need to predict new experimental data, and you need to have a low uncertainty. So this is what I talked about so far. And the final thing is that you need to use your engineering judgment to see that it's close to the place where you validated it. So the place where you're using the model needs to be close to where you validated the model. So if you look here at one of our digital twins, here you have data and simulation for blood sugar meal responses, you have estimation data, you have validation data. So here you did the validation for the lunch response, you estimate for the breakfast response. Then you can use the model for a dinner response, because that's a very similar application, even though it's a little bit away. And in our model we have all sorts of other things as well, and you can use this to improve pedagogics, better compliance and prevention and so on. So if you want to see our digital twin, there are lots of videos online that illustrate what we can do. So finally, summary and final point. Uncertainty in model analysis comes from uncertainty of data and is model specific. So different models will give different results. If you don't do uncertainty analysis, you can't draw any strong conclusions. You can't do any of those things that I've said here, so as experiment design, for instance. So if you have well-determined predictions, so core predictions, you can test a model or discriminate between models if they are well-determined and different. And if you want to identify the parameters, you should use uncertain predictions. If you can, use profile likelihood, either otherwise MCMC or bootstrapping. don't use Fisher information matrix or structured identifiability analysis. And make sure that the usage of the well-determined model predictions is close to the context of use where you have validated the model. So that was it for my presentation. Here are some of the funders and some of the key collaborators.